Today, we are going on an incredible journey. We're going to follow a single packet of sunlight on its 93 million mile trip to Earth. But you know what? The journey isn't even close to over when it gets here. It first has to make it through one of the most complex, most important filters in the entire universe, our atmosphere.
So, if you really want to understand our climate, our weather, even just the color of the sky, you have to stop thinking of the atmosphere as empty space. Think of it more like an active, really selective gatekeeper. It's picky. It lets some energy in, it blocks other energy, and it actually traps some on its way out.
Okay, so before we follow our little packet of sunlight, we really need to meet the two main characters in this whole story. First, you've got the energy arriving from the sun, and then you have the energy that's trying to leave Earth. And as you're about to see, they are completely different.
So here's the absolute key difference. Because the sun is unbelievably hot, it blasts out this high-energy, short-wave radiation. Think of it like a powerful, super-focused laser beam. Our Earth, on the other hand, is way cooler, so it gives off this low-energy, long-wave radiation. It's more like a gentle, spread-out warmth. Now this distinction, it's everything. Because our atmospheric gatekeeper treats these two types of energy in totally different ways.
So as that high-energy solar radiation smacks into the top of our atmosphere, it starts this incredibly challenging journey down to the surface. It basically has to run a gauntlet of obstacles, and trust me, not all of it's going to make it. The very first challenge is something called scattering. The light doesn't get absorbed, it just gets knocked off course, bounced around in all directions. And what kind of scattering happens depends completely on the size of the particle the light hits. You've got tiny air molecules causing what's called Rayleigh scattering, then bigger stuff like dust and smoke causes me-scattering. And of course, the big water droplets in clouds, that's non-selective scattering. And this is the crucial part. With Rayleigh scattering, the shorter wavelengths of light, like blue and violet, get scattered way more easily than the longer wavelengths, like red. And folks, this is it. This is the reason our sky is blue. That blue light is just getting pinballed all across the sky by tiny air molecules, while the other colors just keep heading down on a more direct path.
But scattering, believe it or not, is just one of the gauntlet's challenges. A huge amount of energy just gets reflected straight back into space, bounced off things like the bright white tops of clouds. And whatever isn't scattered or reflected might just get absorbed. It's energy captured by gases in the atmosphere before it even gets close to us.
And this brings us to one of the most important jobs our atmosphere has, the ozone layer. Way up in the stratosphere is especially good at absorbing the most harmful, high-energy ultraviolet radiation. It is literally our planet's built-in sunscreen. It's what makes life on the surface even possible.
All right, so what about the energy that actually does make it through this whole gauntlet? The light that finally reaches the ground is what warms our planet. But exactly how that happens really depends on what it hits.
Okay, so once sunlight reaches the surface, we have to talk about something called albedo. The easiest way to think about it is like wearing a white shirt versus a black shirt on a really sunny day. The white shirt reflects sunlight and helps keep you cool. That's high albedo. The black shirt just soaks up the sunlight and gets hot, and that's low albedo. Simple as that.
And you can see this so clearly here. Bright surfaces like fresh snow have a super high albedo. They're like a mirror, just reflecting most of the sun's energy right back out. But then you have dark surfaces, like a deep forest or the ocean. They have a low albedo. They soak up that energy like a sponge. And that absorption is exactly what warms our world.
Now, the energy that's been absorbed by the surface has warmed the Earth. So, naturally, the Earth tries to radiate that energy back out to space as that long-wave infrared heat we talked about. But here's where the story takes a really interesting twist. That return journey, it's not so easy.
This is the famous greenhouse effect, and it's absolutely essential for life. Remember how the atmosphere was mostly transparent to that incoming shortwave sunlight? Well, it turns out it's pretty opaque to the outgoing long-wave heat. Certain gases in the air absorb that outgoing heat, and then they re-radiate it in all directions, including right back down to the surface. It gives the planet an extra cozy blanket of warmth.
So who are these heat-trapping gatekeepers?
Well, it's primarily these gases right here. Water vapor is actually the biggest player, and then you've got carbon dioxide, methane, and a few others. These are the specific molecules in our atmosphere that are just really, really good at grabbing that long-wave infrared energy the Earth is trying to send back out to space.
So let's put all the pieces together, shall we? We've seen the incoming journey and the tricky outgoing journey. When you combine them, what you get is Earth's total energy budget. It's this delicate balance that basically sets our planet's thermostat.
When you look at all the solar energy that reaches us, a pretty big chunk is just immediately reflected away by clouds or the surface itself. Another piece is absorbed directly by the atmosphere. The rest, well, that gets absorbed by the surface, and that's the energy that drives our climate and gets caught in that greenhouse trap.
Ultimately, it's pretty simple. For our planet's temperature to stay stable over the long run, the energy coming in has to equal the energy going out. This entire complex system, the scattering, the reflection, the absorption, and the greenhouse effect, it all works together to try and maintain that perfect equilibrium.
And that, of course, leaves us with a final and pretty critical question. This whole delicate balance is controlled by the precise chemical composition of our atmosphere, by those gatekeepers. So if we change the nature of the gatekeepers, what happens to the balance? And really, that's a question that's going to define our planet's future.